Now it is started. Is it started now?
Yes, sir.
Yes, sir.
Fine. Now just note down key features of the Fourier's law of heat conduction. Number one, it is not an expression that may be derived from the first principles. So it means it is not something like the Bernoulli's equation, which can be thought of as from the first principle, or the conservation of energy principle, like the first law of thermodynamics. It is not like that. Hello.
Screen sharing off.
Screen sharing
Sir,
off.
your screen is not visible.
Just wait.
Sir, screen recording. Recording.
Recording is started, no?
Recording चालू है.
Recording is started. Screen sharing is missing. Now is it okay?
Yes, sir. Yes, sir.
Okay, fine. So these are the key features of the Fourier's law of heat conduction. Number one, I was talking about. It is not an expression that may be derived from first principles. Note down this. I will ask in the oral examination, can it be derived from the first principles? So the answer is no. So the main thing about the Fourier's law is it is generalized based on the experimental evidence or the experimental findings. So this second point. So the Fourier's law is the generalization which is based on the experimental evidence or experimental finding. We saw this in the conduction experiment, steady state conduction experiment, in the previous two, 3 slides, right? Then Fourier's law is an expression that defines the important material property, the thermal conductivity. So if you remember, when we write this expression, that minus k dt by dx, or when we write this expression minus ka dt by dx, if you remember, I already mentioned that this equation is nothing but the definition of the term thermal conductivity. So you can simply write it like this. Correct? Hear me or not? So Fourier's law of heat conduction, what it introduces is the important property of the material, which is the thermal conductivity K. Fine. Now next point. It is a vector expression indicating the heat flux. We know this, and it is normal to the isotherm. We already talked about this, and is in the direction of the decreasing temperature. We know this. Then the next, this is about heat flux, and not about K. And the last point, the Fourier's law applies to all matter regardless of its state, means it is applicable for solid, liquid, or gas. So irrespective of what kind of the matter or a material you have, as long as the conduction phenomenon is occurring, this Fourier's law of heat conduction is applicable. This is what the last point is. Clear? So these are the key features of the Fourier's law. Now can I go to next slide?
Yes, sir.
Hello. Okay, fine. Now
Yes,
take
sir.
down this. As I said in maybe first 2 lectures, we will have the numerical which will test the understanding of your basically the Fourier's equation, as well as the sign convention which we have talked about previously. Means what is the sign convention, how to deal with that minus sign in the Fourier's equation, or what is temperature gradient, what is heat flux, right? So all that stuff will be tested now through this numerical. So it's very simple numerical actually, but it is based on the very basic concepts and the sign conventions. So consider a plain wall 120 mm thick. Means which dimension is 120 mm? Thickness, this dimension, the thickness of the wall, plain wall. So consider a plain wall 120 mm thick, and the thermal conductivity 120 watt per meter K. Steady state conditions are known to exist, means it is problem of steady state conduction. Exists with T1 temperature as 500 K. So this side temperature is 500 K, T1 temperature, which is noted down here, and the T2 temperature is 700 K. Determine the temperature gradient dt by dx and the heat flux q double dash x for the coordinate system shown. This is important. For the coordinate system shown in these three diagrams. Now, if you remember, I already explained that the moment you change the coordinate system, the signs are likely going to change for this dt by dx as well as q double dash x. Clear? To solve this, so I am giving you let us say 2-3 minutes, and in 2-3 minutes you should be in position to solve this. So very simple. You have to find out the temperature gradient dt by dx, and once you know the temperature gradient, then you can simply find out what is this heat flux q double dash x. So we know how to find out the temperature gradient. How will find out temperature gradient dt by dx? It will be
32 minus T1 by X.
I am writing in general here, like this, right?
Hello.
Yes.
So find out. So find out what is dt by dx for case A, and what is q double dash x for case A, and then similarly find out for case B and C. Pay attention to the temperature profile, which is linear. Look at the slope, and also pay attention to the coordinate system. So in first case, this x is positive along right hand side, and in case B, this is positive along left hand side, and same is true about the third diagram. All these three diagrams are different. You may say that these two temperature profiles are one and the same, but the coordinate system is changed here, and here altogether this can be thought of as the mirror image of this, or not? Find out. Once you are ready with the answer, tell me. I will go to the next slide. I am more interested in knowing the signs rather than the values. So finding out the numbers is a bit simple, nothing big in this.
A and C will be positive.
Hello.
A and C are positive and B negative.
Just a minute.
A and C positive, B negative.
Just a minute. Tell me one by one. For case A, dt by dx is
Positive.
166.
positive. And for qx double dot?
Negative.
Is negative. Okay. For case B?
Negative.
What?
Negative.
dt by dx.
Okay. And what about qx double dot?
Positive.
Positive.
For case 3?
dt by dx is positive.
For dt by dx positive.
So this will be negative.
Negative.
Correct? If you look at your calculations, now you will come to know, irrespective of the orientation of your axis, you have used same expression or not?
Yes, sir. Values are same, sir.
Values are same. I am not interested in values. What I am talking about is, irrespective of the orientation of this axis, you have used same expression. Q is equal to, or Q double dot is equal to minus K dt by dx, right? You have used same expression everywhere, or not?
Yes, sir. Same expression.
Yes,
You have
sir.
applied the same content to all, irrespective of the direction of the x-axis. So you understood why that minus sign we have introduced in the Fourier equation. I repeat, we want heat flux positive in positive x direction. Now look at the answer. For case A, you will find it as 2000 plus, as you said, yeah, this is minus. For case B, this is minus, this is plus. And for case C, again, this is plus, and this is minus, right? Is that correct? Same values you are getting or something else?
No, sir. Something else.
Because this data is changed. So tell me, what is the value for first case of dt by dx? So it is 700 minus 500. 700 minus 500 divided by what is length or thickness?
120.
120. Okay, fine. Now I want you to I want you to make the correction in such a way that change this length so that your answer will match with these values. Fine. Do it as a home exercise. Clear?
Yes, sir.
So for example, if you take this as 100, this will turn out to be 2000, I guess. Correct?
Yes, sir.
So idea behind discussing this numerical was to make you understand the sign convention and not the values. Correct? So I hope you understood it. Sign convention. Now can I go to next slide?
Yes, sir.
Now, as we said, the most important property of the material which is introduced through the Fourier's law of heat conduction is the thermal conductivity. Now look at the definition of the thermal conductivity. This is written based on your Fourier's equation itself. So K to the suffix x, this is approximately equal to the minus sign then Q double dash x divided by the temperature gradient dou T by dou x. Now this is written using the Fourier's equation itself. Now for an isotropic material, Kx stands for thermal conductivity along x direction, right? Similarly, I can have the values like Ky, Kz, thermal conductivity along y and z directions, right? So if I have isotropic material, then the thermal conductivity along any direction is one and the same. So isotropic material meaning is, suppose I have a slab like this of some material, and I am taking one point here, right? So if I talk about the thermal conductivity at this particular location along any direction like this, x, y, or z, any direction for that matter, this value is same, K is same. So that kind of material is called as an isotropic material. Does it make sense? Hello? Is it clear what we mean by isotropic material? Now, see, K may be function of temperature. Now in the same material, at this point, K may be different than this. So here it can be K dash, right? Because I have changed the position, right? And as I said, the thermal conductivity may be a function of temperature. So let us assume in this case, the temperature will be different at this location. So K might be different at this point. But at this particular location, it will be same in all directions. So that is isotropic material. Is it clear definition of isotropic material?
Yes, sir. We got.
Don't be under impression that K will be same right from this to this end. Don't be under that impression. Meaning of isotropic is at a particular point it will be same in all directions. So directional aspect. So that's why I'm writing this Kx is equal to Ky is equal to Kz is equal to K. in most of the situations, this assumption is valid, and we will deal with this kind of material only, that is isotropic material. Fine. Now look at the bullets which are given below. For a prescribed temperature gradient means for given value of this dt by dx or dou t by dou x for that matter, the conduction heat flux increases with increasing thermal conductivity. It means for given value of dou t by dou x, if you fix this denominator, if k increases, this qx double dot will also increase, or reverse is true. That's what the meaning of the first bullet. For a prescribed temperature gradient, the conduction heat flux increases with increasing thermal conductivity. Now, second point. In general, the thermal conductivity of a solid is larger than that of a liquid, and which is larger than a gas. So, K for solid is greater than K for liquid and is greater than K for gas. So, this is what the general trend is. Second point. Now, the last point, the thermal conductivity of a solid may be more than 4 orders of magnitude larger than that of a gas. So, for example, if you look at this plot, take any gas, maybe carbon dioxide. So, look at the thermal conductivity, it is close to 0.01, fine. And then you take the metal or a solid somewhere in this zone, you will find typically this is of the order of 10 raised to the power 4 more than this value. Getting me or not? Close to 100 now. Is it clear? Last point.
Yes, sir. Sir, can you tell the prescribed temperature gradient, sir, once again?
See, what we mean by prescribed temperature gradient means I am fixing this value dou t by dou x. I am keeping it constant. Something like, let us say, if I say minus 300 degrees centigrade per meter. So this value I am fixing. So for fixed value of this denominator, this qx double dot will increase with increase in thermal conductivity. This is what it says. Means if I take two different materials and keep the temperature gradient same, then this as the k will be different for the materials, this qx will also be different. Get me or not? So if I increase k, then the qx double dash will also increase. So if I have the thermal conductivity 1 and the corresponding let us say qx double dot as 10 for let us say plastic, these values are not true, I am just giving an example. And if I make this k equal to 100, then the corresponding qx double dot will also be more. Getting me or not? So it means the heat flux is has direct connection with the value of thermal conductivity. So you can say higher the thermal conductivity, higher will be the heat flux, something like that, for a given temperature gradient or for a prescribed temperature gradient. Is it clear? Hello.
Yes, sir.
So you should understand this plot and just look at the range of thermal conductivity, how it ranges. So right from 0.01 to 1000, the scale is given. And on this side, you will find the gases which have the very low thermal conductivity. Then in between, you will find liquids. And at the end, you will find here the metals, right? And before metals, you will find alloys also in this zone. Because alloy is again the combination of the pure materials, right? So if you compare pure materials, pure metals with the alloys, the thermal conductivity of pure metals will be more than the alloys, right? So you should remember this range. That is what is expected from this slide. Fine. Now can I go to next slide?
Yes, sir.
Now just look at the nature of how K varies with temperature. So this plot is for the temperature dependence of thermal conductivity K. As I said before, K is function of temperature. So how K varies with respect to temperature T. This is what the plot is all about. And we have three plots like this. This is current is for solid, Similar kind of plots will be there for the liquids and gases. I want you to just look at the trend and the range of thermal conductivity. See, the temperature on the plot is from 100 K to 4000 K they have taken, and then look at the nature of this graph, these falling lines, right? And there are a few exceptions where the lines are rising. For example, this one, that in case of stainless steel, this material AISI 304, with increase in temperature there is increase in thermal conductivity. Whereas for most of the metals, if you see from top, like silver, copper, gold, aluminium, or aluminium alloys also, the typical nature, or iron, the typical trend is for the metals, with increase in temperature there is decrease in thermal conductivity. So this typical nature I want you to understand. Clear? This for the solids. Hello. So in solids you can take metals, non-metals, and alloys, things like maybe plastic or wood, all materials which are solids you can think about. Whereas the thermal conductivity for wood will be very low than this. Those curves may not be covered in this type of diagram right now. So understood the trend, how the thermal conductivity for solids varies with respect to temperature. I will ask a lot of questions on this in oral also. I want you to dig deep inside this and just find out how the temperature affects the thermal conductivity of a material or solid. Now, similarly, we have the one more plot for how K varies with temperature in case of the gases. In case of the gases, so you will see the typical gases like, or commonly used gases like hydrogen is there, helium is there, then the air, the carbon dioxide, and the steam or a water vapor, right? So 5 typical plots you can see. So what is common in all these plots is, with increase in temperature, what is happening to the thermal conductivity? Hello?
Increasing with respect to the temperature.
So with increase in temperature, thermal conductivity is also increasing, right? And if you observe carefully these two gases, hydrogen and helium, and compare these two with the remaining, the air, carbon dioxide, and steam, what you will observe is the increase is not that much steep for these materials compared to the hydrogen and helium. Correct? So for a hydrogen and helium, with a small increase in temperature, there is large increase in thermal conductivity. So the slope of this, these two lines are more steep compared to this. So you should understand this. Huh? Now, can I go to next slide?
Yes, sir.
Now the last plot, this is for the some of the selected non-metallic liquids, and the common liquids like the water or the glycerin. So what you see is there is no clear-cut, what you can say, the trend when you talk about the effect of temperature on thermal conductivity of the liquids. And remember, this is under the saturated conditions. All these liquids are under the saturated situation. Remember this. So if I talk about, let us say, the engine oil, then this straight line indicates that there is not much effect on the thermal conductivity of the engine oil when you change the temperature, maybe from 250 Kelvin to even up to the 500 K. This is what we can see from the plot, right? As the straight line. So if you talk about the ammonia, then the tendency is with increase in temperature, there is decrease in the thermal conductivity. If you look at the water, for some part, when you increase the temperature, there is increase in thermal conductivity, maybe up to this temperature, which is close to this value, somewhere around 420 K, right? This is 450, let us say. So somewhere around 420 K, you will find that the conductivity is maximum. And then if you go on increasing the temperature, the thermal conductivity may decrease. So this is what the nature for water. And for the refrigerants like Freon 12, again the similar kind of plot is there. that with increase in temperature there is decrease in the thermal conductivity, but this decrease is slight compared to the decrease in thermal conductivity of ammonia. So this is not the steep curve, this is somewhat flat compared to the nature of the ammonia. And for the material like glycerin, you will observe that with increase in temperature there is slight increase in the thermal conductivity. So this slightly rising curve indicates the small increase in the thermal conductivity for the temperature, increase in temperature. So these two you should be able to compare. Then these two, and water has got the altogether different kind of variation. That it means initially it increases and then it decreases with increase in temperature. Fine. However, this is very brief introduction or the idea about how the thermal conductivity K varies with temperature. However, students are advised to refer the standard text and read more about how temperature affects the thermal conductivity of the different kinds of materials. Fine. All those details cannot be covered in this introductory kind of the course on heat transfer. So I leave it to the students to explore further on this part. Now, can I go to next slide? Hello.
Yes. Yes.
Okay, fine. Now, apart from the most important property of the material, that is thermal conductivity, now we'll introduce a few more properties. So other relevant properties which we are going to use throughout our course on conduction. So I have classified this as the thermophysical properties. Thermophysical properties, right? So the thermophysical properties, again I am further expanding it as the transport properties, means which are the responsible for the transport, means changing the position from one to other, one position to another position. So transport properties, and then second is the pure thermodynamic properties. You have studied thermodynamic properties in thermodynamics, right? And some of the transport properties we have studied in fluid mechanics as well, right? So the first transport property we already talked about, this thermal conductivity K, which is responsible for the heat transfer, right, by conduction. And the second transport property, the kinematic viscosity, I am using symbol nu, Greek symbol nu. Now this is responsible for the momentum transfer. We have studied this in fluid mechanics. Do you remember or not? Kinematic viscosity. Hello.
Yes, sir. Sir,
So the kinematic viscosity deals with the momentum transfer. This thermal conductivity deals with the heat transfer. And on the other side, the thermodynamic properties, we already talked about this density, both in thermodynamics as well as fluid mechanics, right? Then the second property is specific heat. In thermodynamics we studied, and the combination of these two properties, or the product of these two, heat capacity, the rho Cp. There is some background noise. Mute yourself. Hello. So shall I go ahead or not?
Yes, sir. So continue.
Yes. Okay. So now we will introduce one more property apart from K, and that property is called as the thermal diffusivity alpha. I am using symbol alpha. Just note down the definition of this thermal diffusivity as it is, alpha. So the thermal diffusivity is basically the ratio of the thermal conductivity K to the heat capacity of the material rho Cp. So alpha is given as K by rho Cp. Note down this thermal diffusivity. So the characteristic of the material, which will talk about how the heat will be diffused through the material, or how the heat will diffuse within the material, how fast or how slow the process will occur, that will be decided by this term thermal diffusivity. So it is the product of the thermal conductivity, ratio of the thermal conductivity divided by the heat capacity of the material. And the note down the unit of thermal diffusivity is meter square per second. So if you put the units for K, for example, what is the unit of K? What is the unit of K? Thermal
Watt
conductivity?
Meter.
So it will be watt per meter Kelvin. What is the unit of density?
kg per meter cube.
Kg per meter cube. And what is the unit of Cp?
Joule per kg.
Joule per kg K or kilojoule per kg K, whatever you want, you can use, right? So you are using watt here, so they should be in joule. If it is kilowatt, you can use in kilojoule, right? And if you solve these units, you will get that the unit of thermal diffusivity is meter square per second. Correct? Now, is there any other quantity in fluid mechanics which has got the same unit, meter square per second?
Sorry, sir, can you repeat, please?
There is one more property in fluid mechanics which has got the same unit as that of thermal diffusivity. What is the unit of kinematic viscosity? Unit of this quantity? Is it meter square per second?
Yes.
Do you remember or not? So the unit of kinematic viscosity is meter square per second. So it talks about the momentum transfer. So similarly, in case of the heat transfer, this term thermal diffusivity is pretty analogous to the kinematic viscosity term nu. So understand this part.
Yes, sir, got it.
So based on the values of these two, we are going to introduce some dimensionless numbers also in future, maybe in convection part. So again, we will reintroduce these terms, thermal diffusivity and the kinematic viscosity during this discussion on convection. Now moving further, the most important part of today's session, that is, we will try to derive the heat conduction equation or the heat diffusion equation basically. So the question which arises is why to carry out the conduction analysis? Why conduction analysis is required? Why to do this? So there are the 4 points which are listed here, which will answer your query, why to carry out the conduction analysis or the reasoning behind. So the first point, what we will do by the analysis is know the temperature distribution, which represents how the temperature varies with position in the medium. So our intention is to look at how the temperature is varying, let us say along this slab maybe, right? So idea is to know the temperature distribution within this material, right? Then second point, the compute conduction heat flux at any point. So if I give you any point like this, you should be in position to find out what is the conduction heat flux Qx double dash, right? At any point in the medium or on its surface using the Fourier's law. So we know along with the Fourier's law, you will be in position to find out this the conduction heat flux, right? So three things we talked about: temperature distribution, then this heat flux, calculation of heat flux, and the Fourier's law. Fourier's law. These three will go together, right? Then next point, other important quantities of interest may also be determined. Now, what are the other quantities of interest? For example, they have given the knowledge of the temperature distribution could be used to find out structural integrity through determination of thermal stresses. So you can find out the thermal stresses, how they are distributed throughout the material. Is there any stress concentration happening? Because that will give you the indication of maybe the failure in the material, how the failure in the material may take place. If there is some stress concentration happening in a particular zone, then that indicates the that ideally or typically the failure may take place in that zone of the material, right? It also will give you idea about these terms like thermal expansion or the deflection, something like that. So why temperature distribution is required? The answer is this. And the last point, the temperature distribution could also be used to optimize the thickness of an insulating material or to determine the compatibility of special coatings or adhesives used with the material. Means if you know the temperature distribution, you can decide on what exact thickness you have to apply for the material so that the insulation is effective, right? So the temperature distribution will give you an idea about optimization, or will help you in optimizing the thickness of the insulation, or will also help you in deciding on the thickness of the coating which you should use, right? So the most important part of the analysis, conduction analysis, is the temperature distribution. Remember this. Now, moving further, we'll try to derive this heat diffusion equation or the heat conduction equation in Cartesian coordinates. Fine. Now, to do that, what I will start from is, I'm considering a domain like this, right? And within this domain, I'm selecting element like this, which looks like a cube. So I'm taking this element here, and the way you did this, the analysis in fluid mechanics, how you derived the contour equation, if you remember, in 3 dimensions. Similar kind of approach we are going to use here. Only thing is, there it was the law of conservation of mass. Here we'll talk about the energy, basically, or the rates of energy flowing in and flowing out of this control volume. So consider this is like a control volume, right? Along x, y, and z directions, the dimensions of the element are given, dx, dy, and dz, along 3 coordinate directions, which is shown here. Then these 3 points. So we will consider the material is homogeneous. There are no variations within the space. Properties remain same. So the homogeneous medium within which there is no bulk motion, means the advection is absent. There is no bulk motion of the particles taking place or the molecules taking place in this. No bulk motion. So that kind of material we are talking about. Then the second point, the temperature distribution T as a function of x, y, and z, 3 coordinate directions. The temperature distribution T, x, y, z is expressed in Cartesian coordinates. So x, y, z are Cartesian coordinates. The coordinate system is shown here, right? Second. And the last one, we are talking about the infinitesimally small differential control volume or the element like this, and having the dimensions dx, dy, and dz. So the product of these is nothing but the volume of this element or the control volume. Clear? Now, I have used the notation 1 to indicate what is the heat, the rate of heat transfer through the phase inside the control volume. For example, Qx is the heat transfer or the rate of heat transfer through this phase along x direction. Similarly, Qx plus dx is the rate of heat transfer out of the control volume from this phase. So Qx, Qy, and Qz are the rate of heat transfer entering the control volume from x, y, and z direction. So all these 3 terms together, I am calling it as equation 1, right? And then these 3 terms, the heat transfer rates going out from the coordinate axis x, y, and z, these 3 terms together, I am noting it down as the equation 2. Now, how to find out these terms? What is the expression I am using here actually? Which expansion series I am using? The Taylor series expansion actually. So Qx plus dx is the rate of heat transfer from this phase going out. So I am writing this using the Taylor series expansion, neglecting higher order terms. So this is written as the Qx plus dou by dou x, because this is Qx is changing along x direction. So dou by dou x of Qx multiplied by the distance through which this change is occurring. So the distance is between this phase and this phase is dx. So Qx plus dou Qx by dou x into dx will give you this quantity Qx plus dx, the rate of heat transfer out of the control volume from the right phase, which is normal to the x direction. Similarly, the other 2 quantities Qy plus dy and Qz plus dz. Are you getting my point or not? So note down these as it is. Hello? Are you getting this or not?
Yes, sir.
Write down quickly.
So can you please take back to previous slide just once a second? Yeah, sir, done, sir. Thank you, sir.
Note down this Qx plus dx, Qy plus dy, Qz plus dz expression, and look at the equation numbers. Equation 1 is Qx, Qy, Qz, which are the rate of heat transfer entering the control volume along x, y, and z directions, and Qx plus dx, Qy plus dy, and Qz plus dz are the rate of heat transfer going out of the control volume from coordinate directions x, y, and z respectively. Fine. Now moving further, what we are going to do is we will simply write the energy balance. Now what are these quantities? E dot G and E dot ST. We will introduce in the next slide these two quantities. So G stands for the generation and ST stands for the storage. So this is the rate of energy generation. Dot indicates the rate. Dot indicates the rate. So this is the rate of energy storage. So what are these two quantities? We'll introduce here. Now look at the next slide. So within the medium, there may also be the energy source term, which is associated with the internal energy generation or the internal heat generation, you can call it as. So that term is given by this expression. So E dot G is the energy generation within the material. So E dot G is equal to Q dot into dx dy dz. Note down this as equation 3, where we have introduced one more term Q dot. Now what is this Q dot? So I write down the expression which we are using for Q dot, or the notation. Q dot indicates the rate at which energy is generated per net volume of the medium. It means Q dash is, I can call it as a volumetric heat generation, volumetric heat generation rate, volumetric heat generation rate. It means this Q dot is your Q divided by volume, volumetric heat generation rate. So that's why the unit is watt per meter cube. Unit of Q dot is watt per meter cube. So volumetric heat generation rate. So if you have noted down equation 3, then we'll move further. So next point is, if the material is not experiencing any change in phase, like boiling or condensation, something like that. So if material is not experiencing that kind of phase change, then the latent energy effects are not pertinent. So we'll only talk about the sensible energy, and the energy storage term reduces to the rate of change of sensible energy only. So that's why the second term, this is the energy generation term. Energy storage term within the control volume, E dot ST, will be written using this expression. So in absence of phase change, I can write it as the rate of change of the sensible heat within the material. So that's why dou by dou T of U sensible, which is the internal energy of sensible energy, nothing but the internal energy of the material, right? Hello, is that clear? So if you expand this term further, you can write the energy storage term as rho Cv dou T by dou T into dx dy dz. Is it clear? Hello.
Yes, sir.
So you must have used how to find out this change, how to write this term du or u in case of thermodynamics. You have learned. So you used to write it as mCv dt, or if it is the rate divided by time, then you may write it like m dot Cv dt, something like this, right? M dot Cv dt, correct? So this m dot is what? So density into the volume, or not? Density into volume. So this is how density into this volume term is there, so rho into this. So this expression is something like this m dot Cv dt, similar to this. Fine. And for incompressible substance, we know that Cp and Cv both are one and the same. So I can just replace the Cv by Cp and rewrite the same expression as rho Cp dou T by dou T into dx dy dz. Now remember, why we are writing this term dx dy dz together here is, we know this is volume of the element, or the volume of the control volume which we have selected. So energy storage term is given by this expression, rho Cp dou T by dou T into dx dy dz. Is it clear? Hello.
Yes, sir.
Okay, fine. Now moving further, on the next slide, what we will do is we will simply write the energy balance and nothing else. So we talked about the energy entering the control volume through the three phases and the energy leaving the control volume through the other three phases along XYZ direction, and two more terms, the energy stored within the control volume and the energy generation within the control volume, right? So here is the energy balance now. This is the law of conservation of energy, basically, this equation. So on the rate basis, I can write, rate basis means per unit time. That's why this dot is there. So E by T is nothing but, or d by dt is nothing but E dot. So E dot in plus E dot G. So this is your control volume. This is E dot in, and here is the term E dot G minus this E dot out, minus E dot out. If you write the energy balance with these three, then whatever remains is nothing but the energy stored, E dot St. So this is how the energy balance is written. Write down this equation as it is. E dot in plus E dot G minus E dot out, this must be equal to E dot St. And name this as equation 5. As it were? Hello?
Yes, sir, we are doing.
Okay, fine. Now, you remember what is equation 1? Equation 1 talks about Qx, Qy, Qz. Qx, Qy, Qz. Equation 2 talks about Qx plus dx, Qy plus dy, and Q z plus dz, right? Equation 3 is which term? The generation term. Equation 4 is the storage term, and equation 5 is your energy balance at the end. So if you put these four equations 1, 2, 3, 4 in this equation 5 and solve it further, now I am skipping the terms in between. I am not writing those terms. So you can simply write Qx plus Qy plus Qz plus Q dot into dx dy dz minus Qx plus dx minus Qy plus dy minus Qz plus dz. This must be equal to rho Cp dot T by dot T into dx dy dz, the volume of the element, right? And name this as equation 6. Now, if you put the expression for these three terms, like we know what is Qx plus dx. Qx plus dx is Qx plus dou by dou x of Qx into dx. We know this. So if you substitute those expressions here for 1, 2, and this 3 term and solve it further, then equation 6 will get reduced to equation 7. So write down the equation 7, which is minus dou by dou x of Qx into dx plus minus dou by dou y of Qy into dy plus minus dou by dou z of Qz into dz plus this term will remain as it is, this one, Q dot dx dy dz plus the right hand side will remain as it is, rho Cp dot T by dot T dx dy dz, right? And now I am introducing the Fourier's law here. So how to write this term Qx, Qy, and Qz using Fourier's law? We know that. So the same definitions I am introducing here. Qx is minus Ka. This is actually A. The area which is normal to x-axis. This is the area A which is normal to y-axis, and this is area A which is normal to the z-axis. So all these expressions are one and the same: minus Ka dt by dx, minus Ka dt by dy, minus Ka dt by dz for Qx, Qy, and Qz. So if I substitute these three expressions, I am calling it as equation 8 in equation 7 here. So I have to replace these terms. These three, and then solve this expression or equation further. Then what will we get is shown in the next slide. Can I go to next slide now? Hello?
Yes, sir.
Yes, sir.
Okay, fine. So once you put all those expressions, you will get this equation. So substituting equation 8 into equation 7 and dividing throughout by the volume of the element or the control volume, which is dx dy dz, you will simplify the equation further and write down equation 9, which reads as dou by dou x of k into dou t by dou s plus dou by dou f k into dou t by dou y plus dou by dou z of k into dou t by dou z plus q dot must be equal to rho Cp dou t by dou t. So this is our equation 9. Now remember, here we have kept k inside the derivative. It means this k is function of x, this k is function of y, and k is function of z. So in this equation, we have not assumed this situation, kx equal to ky equal to kz equal to k. This is not applicable here. We have considered k as a variable with respect to space coordinate. Means k is varying throughout the material. This is what we have assumed. Is it clear? Now, I can simplify this equation further. So if the thermal conductivity k is assumed to be constant, then you can simply take it out of the derivative and take it on the or divide the entire expression by k and write down this expression. So divide this whole expression by the thermal conductivity k. So the left hand side will be reduced to dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus this q dot by k. This must be equal to 1 by alpha dou t by dou t. So this is our equation 10. Name it as equation 10. So equation 9 is the most general form of the heat conduction equation in Cartesian coordinates. I said the most general form of the heat conduction equation in Cartesian coordinates is equation 9, where all the terms are intact or kept as they are. Nothing is simplified from equation 9. Equation 9 onward, we are making the simplifications, or we are introducing the assumptions. Fine. So now next, if you consider the steady state condition, then this term will go. So under the steady state conditions, you can say that there is no change in the amount of energy storage. This E dot storage, this term will be 0 under steady state, because whatever energy is coming in will go out from the control volume, and nothing will be stored inside the control volume. So that kind of scenario. That means this term will become 0. So if this term becomes 0, and apart from that, if I keep k as a variable, then using the steady state and considering k as the variable, this equation will be further reduced. Equation 9 will be further reduced to this form. So dou by dou x of k dot t by dou x plus dou by dou of k dot t by dou y plus dou by dou z of k dot t by dou z plus q dot must be equal to 0. Clear? Note down equation 11 as well. And now the last simplification. If the heat transfer is one-dimensional, let us assume that the one-dimensional heat conduction in case of slab, heat is transferred along x direction only. So q is function of x alone, right? So in that case, t will also be function of x alone. So the moment I say t is function of x alone, this dou will be replaced by d. The partial derivative will be replaced by total derivative, complete derivative. So and there is no internal heat generation. So this term will become 0, and these two terms will be 0 for one-dimensional heat conduction, assuming heat conduction along x direction. So only this term will remain. So I am simplifying this term further as d by dx of k dt by dx is equal to 0. And I can simplify this further. Note down this as equation 12. And if I simplify this further, saying that k is constant, then the same expression can be written as d square t by dx square is equal to 0. The simplest form of the heat conduction equation is this: d square t by dx square is equal to 0. So remember, the heat conduction equation is the second order differential equation, right? Second order differential equation. So it means it requires at least two conditions to, or two boundary conditions should be known to you, so as to solve this equation and get the temperature distribution from this. Have you noted down all these equations? Follow?
Yes.
So have you understood how we derived this, the approach used?
Yes.
Now, using the same approach, you should be in position to derive the heat conduction equation for the cylindrical and the spherical coordinate systems as well. So will you do it on your own? The heat conduction equation in case of cylindrical and spherical coordinate systems? Huh? Hello?
Yes, sir.
What happened?
So we will try at home.
At least try. The approach is same. Irrespective of your coordinate system, approach is one and the same. The only thing is the geometry or the element will change, and how you write the terms, that is the heat transfer rates entering and leaving the control volume along the directions, like in case of cylindrical coordinates, you have to write how the quantities are entering and leaving along the R direction, that is radial direction, then the Z direction, which is the axis of the cylinder, and the phi, the angular direction. So how you write the variation along R, phi or theta and Z directions, you have to look at. And for spherical coordinates, along with the radial direction, you have two more angular directions, theta and phi. So how you write the quantities entering and leaving the element or the control volume, how you select the control volume is more important. Whereas the basic approach will remain same as similar to your Cartesian coordinate.